know that palm oil effluent and microalgae can be used to produce hydrogen? We're from Fykia E and we will showcase how this concept can be innovated into a conceptual idea. But first, let's understand why this is important.
Palm oil meal effluent, or POME, is one of Malaysia's largest agricultural waste that can cause serious environmental challenges if not properly managed. At the same time, microalgae is an emerging sustainable pathway for hydrogen production, yet it still remains largely underutilized. Our solution integrates both, converting POME into biohydrogen through microalgae-based processes, creating a scalable, cost-effective, and environmental-friendly alternative to conventional fuel-based hydrogen.
We have talked about the why, now let's dive into the most anticipated part, the how. Here's the blueprint for solving the energy crisis.
To produce biohydrogen, we employ a two-stage process. First stage, upstream treatment and dark fermentation. First, raw POME is neutralized and treated with activated carbon to reduce turbidity and BOD level. In an anaerobic digester, dark fermentation breaks down the organic matter to release the first yield of hydrogen. The effluent is then clarified and diluted to approximately 30% to ensure light penetration. Moving on to the second stage, midstream algal photolysis. We inoculate the medium with Chlamydomonas reinhardtii, chosen for its efficient iron-iron hydrogenase enzyme. By removing sulfur from the photobioreactor, we induce the anaerobic conditions needed to activate these enzymes. Finally, under sufficient light, the algae perform photolysis to extract the second stream of hydrogen.
To solve the storage challenge in Malaysia, we transform the biohydrogen to green ammonia. First, capture the nitrogen from atmosphere through the PSA unit, then combine the biohydrogen with the captured nitrogen via the Haber-Bosch reactor. Then, liquefy the ammonia in 10 bars and store it directly to the tank for future use.
Now we'll use calculations to estimate the amount of biohydrogen that can be produced from POME. So in general, this POME has a chemical oxygen demand (COD) level of around 0.051 kg per liter. By using a hydrogen yield of 8 to 16 moles per kilogram of COD removed, we obtain 0.408 to 0.816 moles of hydrogen per liter of POME. At standard conditions, this corresponds to about 9.14 to 18.28 liters of hydrogen produced per liter of POME. So this demonstrates a strong potential for biohydrogen production from POME via dark fermentation process. Now let us apply the previous hydrogen yield for scaling up calculations in a palm oil mill that operates 60 hours per day. According to Sabah Environment Protection Department, processing 1 ton of fresh fruit bunch FFB will produce 0.7 cubic meter of POME per day. This will produce around 740 cubic meters of POME per day. And using our earlier hydrogen yield calculations, this can produce approximately 6.77 to 13.5 million liters of hydrogen per day. This shows a strong scalability at industrial level in a palm oil mill.
POME is a high organic wastewater that can release methane and causes severe water pollution if untreated. Our approach converts POME into biohydrogen through biological process. This transforming waste into a valuable energy resource, and this significantly reduces greenhouse gas emissions while producing renewable hydrogen as a clean fuel. At the same time, it promotes waste valorization by turning a low-value waste stream into a high-value energy product.
From a techno-economic perspective, our system uses cost-effective pathway for hydrogen productions. Unlike conventional green hydrogen, use high energy inputs, our process uses POME as a low-cost feedstock.
This significantly reduces production costs while maintaining environmental benefits. Therefore, our solution provides a balanced approach between economic feasibility and sustainability. Malaysia is one of the world's largest palm oil producers, generating a substantial amount of POME annually. This ensures a consistent and abundant feedstock supply for our system. In addition, our solutions support national sustainability goals and the transition toward a low-carbon economy.
Therefore, it's not only feasible but also highly scalable within the Malaysian context.
In conclusion, our innovation demonstrates how by integrating POME treatment with microalgae-based processes, we can kill two birds with one stone. Not only this innovation addresses on environmental pollution, but it also contributes to a cleaner and renewable hydrogen production. Our innovation offers a more cost-effective and scalable pathway towards a sustainable energy and towards a greener future.